Okay, thank you. It's my pleasant duty to introduce Cecilia Payne-Gaposchkin, lecturer today. And usually at this point, I give a little capsule history of Cecilia Payne, later on Cecilia Payne-Gaposchkin, and her contribution to astrophysics. I spent a little bit of time on the remarkable introduction of quantum statistics to stellar atmospheres, the recognition that the difference up and down the main sequence was primarily one of temperature rather than composition. And what was played down at the time, but which is perhaps the most remarkable realization, is that the sun is made out of hydrogen with a smattering of everything else. And so I usually spend a certain amount of time on this, and then I discovered just a few hours ago that our speaker has actually read her thesis. And so I'm by no means the most knowledgeable person up here to comment on this.
I'm sure that's true.
But that actually makes it a little easier, because I happen to know that Chuck has a lot to say. Chuck is the Lee A. Dubridge Professor of Astrophysics at Caltech. His research focuses on observational studies of the formation and evolution of galaxies, largely at high redshift, principally using the Keck observatories. And he's been a leader in this field for decades now. And so I could read out the list of accomplishments, including the Gruber Prize, a MacArthur, a Warner, and a Packard Fellowship. I think I'll stop at this point, get out of the way, and let Chuck give his talk. Thank you. That is not my phone.
Is it possible? Yes, perfect. Well, I wanted to, I think it's my duty to say something about Cecilia Payne-Gaposchkin, and that's why I decided I needed to know something so that I'd have something intelligent to say. And I was blown away, actually. I knew she was a famous astronomer, but I was really impressed because I found several places where people had mentioned her PhD thesis as being one of the greatest PhD theses ever written. So I decided that would be worth reading. So it's available, and I have it in my backpack. And it's kind of like how you would go about teaching about stellar atmospheres to someone who knew physics but no astronomy, and it's like incredible. It's like a really, really interesting. I found it to be very interesting, and I think I obviously couldn't review her entire career, and that was the first thing she did. But it was, I like to think of it as the sort of first time that somebody really said, we're going to learn about astrophysics of the universe by looking at spectra. And we can learn almost everything there is to know by looking at spectra. And I think, here's the thesis. It's pretty humbling, looking back at what papers one wrote when one was a graduate student. It's kind of embarrassing. So I just wanted to pay tribute. And when I was thinking about what should I talk about, well, I usually run at the mouth and talk about too many different things because I just. But in this case, it was clear I needed to talk about something having to do with, the chemical abundances. And there are some interesting things to say about that with respect to high redshift galaxies, so I'm going to focus on that today. And I'm going to talk about things that are seen as being very interesting and primarily these days because they give rise to massive binary things that do all sorts of interesting, strange things in the universe, gamma ray bursts, neutron star mergers, all things like that. But from the standpoint of understanding the history of galaxies in the universe, they're pretty important. And the problem is, and I'm going to argue, that there's almost no massive star in the universe now that looks anything like typical massive stars did 10 or 12 billion years ago, and that leads to some confusion because, we sensibly, in most cases, anchor ourselves to things we know at redshift 0 when interpreting the distant universe. And this is a case where maybe that's not quite the right thing to do, or at least you have to make sure you're looking at the right things in the local universe when you do the comparison. So, massive stars do lots of fun things. They produce most of the metals in the history of star formation and galaxies. And if you're interested in galaxy formation, they're really important because they're really bright, so they produce a lot of radiation pressure, stellar winds. The late stages of evolution are important. The core collapse supernovae that are believed to dominate basically stellar feedback processes. And all of this controls how fast a galaxy can accrete, or how fast it can turn stars or gas into stars. And moreover, when we observe the high redshift universe, the bolometric luminosity of galaxies at almost any wavelength where you observe, from the ultraviolet to the submillimeter, you're kind of bolometrically dominated by massive stars, unless there's an AGN. And, well, that makes them important for lots of different reasons. And it's this convenience, they're really easy to observe, that I'm going to make use of today. But it really is kind of, if we look at the local universe, we have the low mass stars that formed during this early history of galaxy formation are sitting around in galaxies in our local universe. And they are clues to what one might have expected to observe when going back and seeing the high mass stars that formed along with them. Somehow this didn't really percolate through in a lot of the early stuff done on high redshift galaxies, which I think is, I'll explain, I think, why that happened, but I'll talk about that some more. One of the things, because we can, is we're going to try to look at, one of the things that we can observe is very bright emission lines produced in nebular regions excited by massive stars, ionized by massive stars. They're probably the brightest spectral features, and they are also producing the far ultraviolet continuum. And by and large, it's the same stars that produce the far UV continuum that's relatively easy to observe at high redshift, and the nebular emission lines, which are also easy. And a successful picture has to better be able to make sense of both of those at the same time. And so that's actually kind of the question that we started looking at. And this is a popular thing to show nowadays, especially because of neutron star mergers, which are talking about things down here. But I'm actually, interested in all the gold elements here, and to some extent, comparison with, iron. So iron is what everybody measures in stars because it's easy, and the spectra are dominated by lines of iron. And it turns out that massive stars don't really care very much about anything except iron in terms of how they behave, what their structure is, what the winds, what their late stages of evolution look like. Most of it depends, to a first approximation, only on iron abundance. And we know, when we look in the local universe, that iron behaves differently from other elements. And unfortunately, when we look at nebulae, we're basically more or less sensitive to oxygen and a few other elements that are important for cooling in ionized gas. And it's a pretty good assumption that where you see stars forming in the local universe, that those have the same abundances relative to the sun. But it's a really, really bad assumption to assume that's the case at high redshift. And I'll try to convince you of that. So here's the famous Mad Owl diagram. That's an inside joke that I usually try to tease Piero Madal with. It's to some extent you can read off what some of the important issues I'm going to talk about are. It's almost like, I don't know if people remember the Monty Python skit about the Brontosaurus, and someone has a theory where it's small on one end, it's big in the middle, and it's small on the other end. Well, it's kind of like that for the star formation history. And you can see that, there's a peak here at about a redshift of 2, and this hatched region is where I'm going to be talking about. And the important thing in the context of this massive star business is really better illustrated with this kind of a plot, which just plots for individual galaxies on average, the ratio between the star formation rate and the already formed stellar mass. And one of the weird things is that once you get above redshift 2, it's kind of constant. And if you just do the math, that it corresponds, this constant here corresponds to an e-folding increasing star formation rate as you go forward in time, with an e-folding time of about 200 million years. So what that tells you is that chemically, stars that form during this period of history in the universe are going to look like primarily only enrichment that happens on timescales shorter than 200 million years, because the iron just never can catch up entirely. And so it's not until you turn the corner and you start having declining star formation histories that novae of type 1a can actually catch up. And so to some extent, everything's going to have, this is where the alpha enhanced stuff is forming, and this is where you start asymptotically approaching solar abundance ratios. To first order, that explains a lot of the problems that have faced understanding the high redshift universe. So here's what we have to look at. We have, if you look in the ultraviolet, you see all these interstellar absorption features that tell you something about how fast gas is moving around. And you can measure now nebular emission features. This is H alpha in the same object, just all shifted to the rest frame of the galaxy. And so you can see that gas is moving around a lot faster than the newly forming stars are likely to be. But it gives you a picture, that kind of tells you about both the gas and the stars in the vicinity of where the stars are forming. We don't know where that stuff is completely, which is a whole other topic. But these are the easiest things to measure. And the problem really is that when we talk about the ultraviolet, we're really talking about the far UV between about, greater than 1,000 angstroms. But what we really like, what the nebulae are responding to, is the extreme ultraviolet, which we can't observe. No one's ever observed an O star below 900 angstroms in the local universe. And this little bit of the spectrum between about 1 and 4 Rydbergs is what controls all the things that are used to measure nebular gas phase properties. And our understanding of this part of the spectrum is entirely theoretical. It's pretty good theory, but it's entirely theoretical. And there's a surprising range of possibilities for what the spectra look like. And this is what controls the ionization of the nebulae. So at intermediate redshift, the idea is, when I say intermediate, used to be high, I guess what I mean is in here somewhere instead of out here. So this is an interesting place to work, but the information content of everything you can learn there is quite a bit more limited. But by and large, this behavior is pretty constant. So it's almost as good to look at things here as here if you want to understand what things look like at very high redshift. You can believe that or not. I'll talk about that more later. But one of the ideas is to try to understand just internally from observations that we can make without reference to the local universe. We can build a framework that makes sense for understanding how to turn things we can observe into things we want to know. And also, how do we make the connection? It's kind of an obvious thing that because of what I mentioned, the fact that the stars are still around, that were part of the same star formation episodes that happened a long time ago, and we have access to them spectroscopically in the local universe. What should we expect things to look like, and how do we draw the connection? And it's also the case that, a lot of is made of the James Webb Space Telescope's power for certain things, particularly with high redshift galaxies, and it's great for the nebular emission part, but not so great for the continuum observations for various reasons. And so you'd kind of like to establish a few baselines to interpret JWST data at redshifts where you can collect everything that's relevant. And that's just... So I'm not going to spend too much time on why choosing a particular redshift makes sense. It's very much driven by practicalities, especially in this redshift range between 2 and 2.6. Anybody who's ever tried to do near-infrared spectroscopy from the ground knows that this is the magic range where you get all these strong nebular emission lines in between the opaque bits of the atmosphere. And so you can actually measure a bunch of things like electron density, ionization, excitation, extinction, star formation rate, kinematics of gas, something about gas phase chemistry. And there's a long history of studies doing this kind of thing for nearby galaxies, which in this case I'm not sure is advantageous, but it's there. And you can observe the rest UV without going into space, which is useful too, because when you get to the rest UV, that's where all these ground state transitions of astrophysically abundant ions have, it's very, very rich astrophysically. And if you get to a place where the intervening neutral hydrogen is not so thick that you can't measure anything, which is what happens as you go out beyond redshifts of 4 or so, it's actually a huge value added. And almost everything that we've done on distant galaxies has been designed around taking advantage of access to information about diffuse gas in the intergalactic medium. And so most of what I'm talking about does not come from the famous, half a dozen fields that everybody points to when you work on high redshift galaxies. Whoops. That's... So this is just, this is a survey, and everything I'm going to talk about is kind of drawn from things that we've put together. It's really taken embarrassingly long to do this, about 10 years or so, to compile all of this information. But most of this complexity of what I'm talking is irrelevant to what I'm going to say, and has more to do with getting a good redshift distribution and having a handy dandy bright quasar for which you can get a really high resolution spectrum in the middle of the field, piercing most of the volume. But really it's a survey that's focused on 2 to 3.5 or so, that happen to have convenient quasars, and where right in the heart is where you can best do these observations through the atmospheric transparency windows. And it was rough going for a long time. I think I have somewhere, yeah. So 10 years ago or 12 years ago, it took I don't even want to say how many nights using the NIRSpec instrument, doing 1 or 2 galaxies at a time, to put this together. This is Dawn Erb's thesis, and Dawn then came here as a CFA fellow. But this is from her thesis, where she showed, based on 100 measurements in the K-band at redshift 2, that there's a similar relationship between mass and gas phase metallicity at redshift 2 as in the local universe from Sloan. It's just kind of offset toward lower abundances at fixed mass. There are even fewer observations where you have to make measurements in separate atmospheric bands, literally 4 at that time at this redshift. And it was kind of strange because all 4 of them were nowhere near the locus that one expected based on the local universe. And that for a long time, I think, was kind of a head scratcher. We have much better statistics now thanks to instruments like MOSFIRE which came online in 2012 and actually made wholesale nebular spectroscopy possible. And so you have a set of galaxies for which you have all this information, the nebular diagnostic lines, and the far UV continuum, which has an almost mind-boggling number of things going on in it, including interstellar absorption lines. You have resonance emission lines like Lyman alpha that's basically a recombination line that then scatters through the interstellar medium before escaping. You have other nebular emission lines in the UV, oxygen 3 and carbon 3. And then you have the stellar photospheric spectrum, which is hiding beneath all that stuff. And those stars are, the light that's producing this part of the spectrum basically has to be the same stars that excites the nebulae that produce these emission lines. And that's it turns out to be fairly important. When you get a lot more data, it becomes clear that, and this is from Alison Strom's thesis at Caltech, finished in 2017, there is a locus at high redshift that sits up here in the notch between the various loci. I'm not even going to try to explain the astrophysical significance of this, just suffice to say for the moment that the locus is similar but different, systematically different in this nitrogen 2 over H alpha versus O3 over H beta diagram, and other similar diagrams are offset. There's a point here that I'm going to talk about a fair amount, because one of the things, the first thing you do when you see all this is say, well, I don't know what this means. What could it possibly mean? Let's try to figure it out. Try a bunch of things, and then finally you say, well, let's stack a whole bunch of these spectra that are drawn from a similar place as this locus and see if we can get something out of it. I wanted to mention that this is maybe the most striking nebular diagnostic that makes very clear the main differences. At fixed, it's really the same stellar mass range that we're looking at in the high redshift universe as SDSS looks at in the low redshift universe, but they're about 10 times stronger at a fixed mass in this O3 over H beta. So basically, the spectra that are ionized, first of all, there has to, the radiation field temperature has to be high enough to produce a lot of oxygen 3. And it turns out that, basically the principal thing that's responsible for this difference is just the hardness of the radiation field. How many 4 Rydberg photons there are compared to 1 Rydberg. And that's partially due to differences in metallicity of the stars. The mass metallicity relation is offset, but it's also due to, that's not enough to explain it. And it's similar in diagrams like this, where SDSS is down here, and most of the things at high redshift are sitting up here somewhere. So things are very different, so let's try to figure out what it is. Well, there's been huge amounts of success studying stellar integrated spectra of nearby stellar populations. People like Charlie Conroy have made a huge amount of progress in essentially fitting models to observe spectra in very with high multidimensional spaces that use every bit of the spectrum to determine it. It's a little bit harder to do that. The spectra are kind of not so great sometimes, and there's a lot of things that are not stellar absorption lines in the spectra. But we thought we'd give it a try with the far UV spectra. And what we're interested in doing is saying, well, what range of stellar population models have any hope of being correct? And then we'll put them in and see if we can make the nebular emission lines once we determine that. So you can get fits to the observed spectrum that are actually pretty good with various flavors of models, more on these later, but it's actually surprisingly good. But the only ones that do okay are the ones that have abundances in the stars, let's call it iron abundance, down around 1/10 solar. So anything more metal rich than that fails a bunch of tests, and I think the most visible, most easily seen is here. These are just, the black is the observed spectrum, and the colored lines are metallicity just under 1/10 solar, just over 1/10, and a little over half. And you can see that all these photospheric absorption lines are much weaker in the observed spectrum than in the in the models that are a half solar. And it turns out you can set a pretty strong upper limit at around 2 or 3/10 of solar for the average spectrum. And this turns out to be true across the board for anything we've been able to observe. You always get a low iron abundance. Now, so we take those low iron abundance models, stick them in as the source in photoionization models, and see if we can match the nebular emission. Well, the range of actual extreme ultraviolet spectra, as I said, are surprisingly broad. And it turns out to matter quite a bit at this point whether your models include binary evolution of massive stars or not. The ones that do not look like these spectra. The ones that do are these up here. And it turns out that the boost in both the hardness of the spectrum and the number of ionizing photons produced per solar mass of star formation makes a really big difference for a lot of things. So in terms of the model, we have observations that allow us to fix the electron density. It's around 300, and that comes from the ratio of the oxygen doublet at 3727. We're able to then normalize the radiation field relative to the gas using the ratio of oxygen 3 to oxygen 2. And all of the models more or less agree with one another for what the locus looks like, and we can pinpoint, based on the observed spectrum, right around in here, which helps. And so then you just mess with the nebular abundances and see if you can match the spectrum. So this is the observation in each case. And you can see the first thing you might try is, well, let's just put in metallicity that is comparable to what we infer for the stars, like 2/10 of solar. Well, it's absolutely hopelessly off. So you put in the stars that we see in the same galaxies, and you look at the predictions, and they all should be in here, and this is actually where the observed point is. But if you crank the oxygen abundance in the nebula up to a half solar, you get a pretty good match for the very hardest spectra that are based on these binary population synthesis models. And the same is true for these other diagnostics, where the observation at the same metallicity as one infers for the stars are just hopelessly wrong. And it's much better if you both have a really hard ionizing spectrum, low iron abundance, and you crank up the oxygen abundance in the nebula by a factor of a few, 3 to 5. The same is true of, this is, a parameter. It's basically the sum of oxygen 2 and oxygen 3 divided by H beta. And you can see the same problem. And it works really well if you just make the abundances higher. Nitrogen to oxygen can be inferred in the same way. And you can actually get carbon to oxygen ratios using far ultraviolet emission, nebular emission lines. And if you just, all the things you can learn from this one composite spectrum of 30 objects is you have this oxygen abundance of half solar and iron abundance of a tenth solar, which, often people say, wait a minute, and I'll talk about this in a minute, but, are you saying, so the models we were using when we the stellar models are using solar abundance ratios, and as are the nebular models. This is just the best we can do to fool the models into doing approximately the right thing, because what you really want is non-solar abundance ratios in the stellar models, and then you don't have to pretend anything. But using a low iron abundance stellar model is much closer to the truth than using a half solar abundance stellar model, which doesn't work at all. The point is that we're not saying that the iron in the stars and the gas has different abundance relative to solar. We're just saying we need to use models that are close approximations to what it would look like if if you could make such models, and I certainly can't do it myself, and I'm not aware of any that are out there yet. And then you can compare these abundance ratios with things we know about the local universe. Here's carbon to oxygen against the, the nebular style of expressing the oxygen abundance, where solar in both is right about here. And you can see that the observed point falls down here, where carbon and also nitrogen are falling in this intermediate region where there's a mix. If you believe the lore of nitrogen enrichment, this is the sort of high mass star formation minimum plateau, and then when you start having secondary nitrogen, you start building this up. And you can see that in terms of the chemistry, these are just where they should be chemically relative to the local. These are all H2 regions in nearby galaxies. The problem is that the manifestation of those abundances in the nebular emission lines is totally different because of the non-solar abundance ratios of the stars. And I'll try to explain that better in a minute. This is maybe the most interesting. The inference, these two things together, if you put it into more of a stellar abundance style of expressing it, 0.6 oxygen to iron, the logarithmic abundance ratio, is very close to what's expected for pure core collapse supernova enrichment. And if you look in the galaxy with a capital G, you can find stars that are in a similar part of the diagram, and they're basically in the bulge, and some things in the thick disk approach that. But the number of bulge stars with oxygen abundances that are reliably measured is very small. You can use other alpha elements like magnesium as a proxy, and it should be close. But wanted to make a direct comparison. So it's maybe not surprising if these stars that we see forming have a similar chemical and star formation history to what the galactic bulge did when it formed. That's what you would expect. So that maybe that's good. There's also been an entirely independent measurement at a similar redshift, but this time looking at low mass stars in a galaxy that's already finished doing what it's going to do. And this is just from a couple years ago, using very, very deep observations of a single, very massive quiescent galaxy at a redshift of 2. And it might surprise you to learn that something with this mass has an iron abundance that's subsolar by 0.3 dex. And it has about the same alpha enhancement as what we see in the star-forming things at the same epoch. So maybe this is not a mistake, and this is actually what the universe looks like. And no, I am not saying that stars and gas have different abundances. For some reason, this is really hard for people to understand, and it's almost always my fault. But to a first approximation, nebula don't care about iron; they only care about oxygen. So they only respond to oxygen abundance. And the massive stars only really care about the iron abundance. And so in principle, you can have stars that look like low metallicity stars ionizing gas that looks like high metallicity gas at the same time. And that's essentially what we're saying is happening. This is just some local alpha to iron as a function of overall stellar metallicity. And again, you know, the most extreme things in our galaxy, this is from apogee, the most extreme things are still not as extreme. And this is probably just because these stars come from lower mass galaxies that, you know, whose star formation histories by the present day had mixed in lots of things happening at later times when alpha enhancements were not as large. And, you know, all of that chemical mixing gives you a sequence of alpha to iron ratios. But if you can catch things as they're forming their one big episode of star formation, you kind of expect core collapse supernova abundance ratios. And that seems to be what we're seeing. And the place to look in the local universe to find such things are the cores of very massive elliptical galaxies, because that's the part of the massive ellipticals that hasn't been polluted with as much so-called accretion of gas-poor satellites. Why am I blanking out? Whatever that accretion is called. Stellar accretion of mostly stars rather than gas. And also, you know, really derfy little things like the progenitors of the halostellar populations also have these alpha to iron ratios close to what we're seeing, except the iron abundances are much lower just because the efficiency of retaining metals is smaller in those things when they form. So maybe it makes sense. And what this basically says is that the local things that you should be looking at to compare to the high redshift galaxies are not the star-forming galaxies at all. So all the SDSS comparisons, well, it's not too much of a surprise that they're like on a different system. They are on a different system. They're completely different in terms of the abundance ratios. Now, what is it that controls the level of this this offset from the local locus in these diagnostic diagrams? Well, if you just these are just two subsamples split down the middle. This is where our stacked spectrum was sitting, and looking at where they fall in terms of mass, star formation rate, and the ratio of the two. And by and large, it's the things that have large specific star formation rates, which is just what you expect. It's the things whose star formation rates are increasing with time. They're going to stay very alpha enhanced for as long as you want to keep it going until the star formation rate starts to decline. And that's the first time that you can actually enrich the gas up to near solar in iron. So it's the large offset. The most offset things are the highest ratio of star formation rate to stellar mass, not surprisingly. So the local universe is down here, where star formation rates on average are declining with about the same time scale. And out here, they're increasing. So they have very different chemistry. I hope that makes sense. So what difference does it make? Why do you care? Well, there are a few reasons you might care. If you care about reionization, it actually makes a big difference that the kinds of things that you need to make the nebular spectra work produce 2 or 3 times more ionizing photons per unit star formation as the models that are used for most of the reionization models to date. So that factor of 2 or 3 means you need like escape fractions that can be lower by that same factor. You get the same output from the galaxy population. It also might mess a few things up, and one of the things that was surprising is everybody thinks, well, I know how to convert an H-alpha luminosity into a star formation rate. Of course, that actually depends on what the ionizing stars look like, the stellar population of the stars responsible for doing the ionizing. And that turns out to differ by a factor of up to 5 between something like a solar metallicity, Bruswell-Charlot 2003 kind of model that is like the most generic thing that people use when they're fitting spectral energy distributions, predicts a ratio that's 5 times lower than the most extreme binary population synthesis model that you need to match some of the highest excitation galaxies at high redshift. So if you're measuring star formation rate based on H alpha, it's extremely stochastic because you need to know what are the stars that are doing that in order to relate it to a formed stellar mass. It's almost as big a problem as having complete ignorance about the initial mass function, but probably a bigger problem because nobody questions the Kennicutt conversion from H alpha to star formation rate, and you should be questioning it at least at high redshift. So you can account completely for this offset by putting the right stars in there. And I want to talk a little bit about, because it affects star formation rates, it also can affect inferred stellar masses from SED fitting. It's the case, it's remarkable that the far ultraviolet spectra look very similar in all of these, in various different models at fixed iron abundance. It's the binary star treatment of binaries or rapid rotation or whatever you want to do to change the way the late stages of massive star evolution go. You have to make everything harder by a lot, and binaries are one way to do it. And you can actually, it makes some sense that this is predicted to be an effect that's more important at lower iron abundance. So it's going to be less important after the peak in the star formation history than it was in the early part of the universe. And everything kind of hangs together. But I happen to be interested in trying to measure ionizing photons coming out of a galaxy, and it'd be awfully nice if we could plug in these models that work where they're well constrained to match spectra that are at slightly higher redshift, where you can actually have hope of observing the leaking Lyman continuum photons getting out of a galaxy. And you could actually solve a few problems at once if you could make that hang together in a way that people would believe. And that's what I'm going to try and show you in what remains of the time. It's not that easy to do because, of course, and the reason that people haven't done this at redshift 6 is because the universe becomes so opaque due to intervening stuff that you just don't have any dynamic range to measure small leaking fluxes below the Lyman edge of galaxies. But at lower redshift like 3, you have some hope that you could do this correction. The problem is it's stochastic. It depends on relatively rare high neutral hydrogen column density systems. And so it's kind of like something that is a picket fence sort of thing where you either have a clear line of sight or you don't, or you have something in between that, you could look at the most leaking possible galaxy in the universe and you could just get unlucky and you can have H1, right here along the line of sight, and it would kill off the signal that you could measure. And so you have to do it statistically, and this means this is one of the instances where stacking spectra is really good, because it turns out you can work out, once you know the statistics of the incidence of neutral hydrogen column density as a function, basically the, what do they call this, the neutral hydrogen distribution function along the line of sight in the intergalactic medium. This is a redshift of appropriate to what I'm talking about, 2.5 to 3. And then you can even, because we've done these galaxy surveys where we have quite a bit of knowledge about the local intergalactic medium thanks to the quasars, we can see how that changes when you go anywhere near a galaxy. So usually when you do this kind of thing, you say, okay, a galaxy is at a random place in the universe. What is the probability that an ionizing photon emitted by that galaxy could be observed by me sitting here? And that, of course, assumes that galaxies don't know anything about the gas distribution in the universe, which we know is not correct. And this enhancement in the amount of neutral hydrogen tries to account all the way down to about 50 kiloparsecs from the galaxy for the excess hydrogen that you find near where galaxies have managed to form. So that it's a correction at the 30% level, but it ends up making somewhat of a difference. So this plot shows why you don't do this at redshift 5. This is just the transmission, the percentiles in transmission of the intervening Lyman alpha forest as a function of redshift. This is where we're trying to make the measurement. By the time you get to redshift of 5, something like 75% of all lines of sight would be impossible to make a measurement even if it were there. So you choose your redshift range. We've chosen it here. And then you choose, and then the smaller you can make the interval over which you're making the measurement, the more sensitive you are, because it turns out that this is a cumulative problem where as you go away from the galaxy, some lines of sight are fairly clean, and you get down to 800 angstroms in the rest frame as you go, as the photons propagate. And you're only reduced by something like a factor of 3 relative to what you started with at the Lyman edge at the galaxy. But when you get to the sort of bottom 25%, you basically have 0. The bottom, this is percentile wise, and it looks like the spectrum in the galaxy's observed frame, or in the rest frame of the emitting galaxy, it might as well have 0 leakage. When you average together 30 of these, it turns out, you can reduce the uncertainty in this correction to about 10% of the overall correction. So if you stack 30 things at the same redshift of similar properties, you can basically eliminate the uncertainty of the intergalactic medium correction. And that's the approach that we've taken. But this is raw. This is from a sample of about 125 very deep spectra. And these are stacked in quartiles. This is quartiles of Lyman alpha equivalent width. And you can see some of the most obvious trends. When the equivalent width of Lyman alpha is very low, that is purely absorption, the interstellar lines are correspondingly strong and deep. And the things that have Lyman alpha strongly in emission have much weaker interstellar lines. They also have much greater signal below the Lyman limit. And this is assuming that the IGM is equally behaved for those two subsets, which seems like a reasonable assumption. Similar with UV luminosity, fainter things have more flux coming out, more ionizing photons escaping than brighter things. Turns out it's more driven by what's going on up here, because this is really telling you about how much of the continuum source is covered by gas that kills off that absorbs ionizing photons. We make this global IGM correction, and the stellar models that we were using, the same models to fit the spectra I told you about earlier, do an amazingly good job of they're normalized out here somewhere, and then they're reddened. And this is basically what you get through the far ultraviolet after you do the IGM correction. And the difference here between that spectrum and this spectrum is essentially the escape fraction of ionizing photons. So if we can measure that in a trustworthy way, we might be able to say something. And this just shows more of the spectrum. It turns out that you need even lower stellar abundances. They can't be higher than they have to be lower than a 10th solar to fit these redshift 3 spectra. But they do a remarkably good job. And it allows you to actually make more elaborate models, which I'll tell you about in just a minute. But there is some really stupid correlation, stupid in the sense that they didn't have to be this simple. This is basically just the observed ratio at 900 angstroms versus 1500, the flux density ratio. And you can see that it's up around 15%, and then all of a sudden, right around L star in the luminosity function, it goes down to 0. When you look at Lyman alpha equivalent width, it's actually well described by a straight line where this ratio is linearly related to the Lyman alpha equivalent width, where it hits 0 where Lyman alpha hits 0. So that's sort of suggestive and not all that surprising, because to get ionizing photons out, you need holes in the gas distribution, and those holes would be really good places to have Lyman alpha photons get out too after bouncing around a little bit. And it turns out that if you just rank things in terms of the fraction of Lyman continuum leakage, the most leaking is up here, and the least leaking is down here. And you can see that there's a sort of an obvious correlation with the depth of these absorption features. So when you cover more of the continuum with neutral hydrogen, that's these yellow and green profiles, you get less and less Lyman continuum, and you get less and less Lyman alpha out. So picture a model that looks kind of like this, and this is from a review article that Don Erb wrote a few years ago. Here's us trying to observe through holes, and Lyman alpha photons have the advantage that they can bounce off the backside of this flow, and they can get a kick, a redshifted kick in velocity when they get emitted back this direction that makes them sail relatively easily by all the neutral hydrogen in here. And so they find the same holes that the Lyman continuum photons, which are forced by radiative transfer to go in a straight line. They don't scatter very easily. They go through the holes, and the Lyman alpha photons bounce, and they make it, a lot of them make it through exactly the same holes. And that way you would get a very strong correlation. And that's what it looks like. Here are just some subsets of the data, just trying to show you how things depend. This is the whole sample. So on average, the absolute escape fraction in a model like that, the number, you take all the ionizing photons produced in the galaxy, the ones that get out are 9%. But if you look at things that have Lyman alpha equivalent widths that are 20 angstroms or larger in the rest frame, it's more like 30%. And so they go basically from 0 to 30%, depending on really easily measurable properties that are much easier to measure than the Lyman continuum. These are just numbers that you can actually measure, and these models are using a simple model of the ISM that absorbs only, maybe this illustrates it better. So you have your observed spectrum, and then you have the unattenuated portion, which is neither absorbed nor reddened by dust. You have this stuff that's forced to go through the interstellar medium. Usually it makes a damped Lyman alpha profile. And then you mix them together in a ratio that produces the observed spectrum, constrained in terms of this Lyman alpha column density by the wings of the damped Lyman alpha system here, and by the depth of these Lyman series lines and the residual Lyman continuum. And when you use all these constraints together and you fit the spectra, you get all these numbers out. The total the neutral hydrogen column density, the covering fraction of that neutral hydrogen, and the absolute escape fraction. And that's what we've done. And it looks kind of like this. This is as a function of Lyman alpha. And you can see, as I said, it goes from 0. This is for bright galaxies, which tend to be fully absorbed in Lyman alpha, to things out here with strong Lyman alpha emission at about 30%. Now, that's still only 30% of the ionizing photons getting out, but that's pretty healthy. You might ask, well, how do you fold this in and calculate the emissivity of all the galaxies, which is what reionization people would like to know. Well, you can you can make a model based on the observed distribution function of equivalent widths, or you can make a model based on the observed luminosity function, and you can integrate over those quantities, and you get, basically, you can predict PDFs for what you're going to measure for the ratio between 900 and 1500 angstrom flux. This is the directly measurable quantity, and this is what you expect for the PDF. It's something like 50% you expect zero leakage, and that's due to either bad luck with the intergalactic medium or galaxies that don't leak anything. And you can see that there's this very broad distribution. The only ones that you can detect directly are the ones way out here in the tail. Everything else requires something that's more sensitive. And it turns out that when you add all those photons together, the galaxies make about 3 times more ionizing photons than the quasars at the same redshift, without integrating down to ridiculous luminosities, which is usually the way you get all your ionizing photons. So the model that works is the same model, these binary population synthesis, or any other model that makes ionizing spectra that look like spectra that you get with such models. You get the magic psi ion that you need to reionize the universe by redshift 6. That's essentially the ratio of the ionizing photons produced against the flux density in the non-ionizing ultraviolet. And you get really simple relationships surprisingly simple, between Lyman continuum escape and the ISM covering fraction. So you can just picture galaxies as being holy, and the holes give rise to strong Lyman alpha emission and strong Lyman continuum emission up to a point. Obviously, if you have a really holy ISM, you can't have really strong Lyman alpha emission because that depends on intercepting all of those ionizing photons. So you expect a peak, and the peak is right about here. And this is what the things that leak are expected to have a distribution of Lyman alpha equivalent width that look like that. So they're peaked around 20 to 40 angstrom equivalent widths, which is good because those are really easy to find. And I think this is good news for a lot of reionization era studies, if you believe it. But the point I really wanted to make is all of this is due to, kind of things that make sense in retrospect, given what we know about metallicity in stars and behavior as a function of star formation history. And it makes sense that things behave this way and make a transition right around the redshift of 2 to slowly asymptotically approaching kind of abundance ratios that you see in galaxies where all the star formation is happening now. And if I wanted to make more strident things that might be more memorable, I like to use this slide for that. I've already said this a few times. So stars care only about iron. Nebula care only about oxygen. This is to 0th order. And so assuming that oxygen over iron is 0 is almost always going to be wrong at high redshift. And that makes a large difference in some cases and a smaller difference in other cases. And massive stars at redshifts greater than 2 have properties that I think are exactly what you would have expected given what we know from the fossil record. But you have to look at the right things in the local universe to get that. And looking at the things that are still forming stars is probably exactly the wrong place to look for the descendants of what is easily seen at high redshift. I think that's all I wanted to say. Thank you.
The talk is open for questions.
I have a question about the first part of your talk. Sure. When you're showing the VPT diagram of the oxygen offset, oxygen over H beta offset.
Right.
Then you show that you measured the density from O2.
Yes.
And you're dealing with integrated quantities. But
Yeah, that's
O2, integrated over the entire galaxy, I mean.
That's right.
And O2 and O3 might not come from the same region. So it may
Yes.
happen that you're measuring
So
density.
it turns out, this is something I meant to say but forgot. Galaxies at high redshift look much more like the spectra of individual H2 regions. So they're much more homogeneous in terms of their ionization properties over the luminous parts than nearby galaxies. You have to worry a lot about just the issue you're mentioning. And in fact, with diffuse interstellar gas, no one really understands what that is, how to deal with it properly. But the comforting thing is that you can use H2 regions quite successfully to model, to match the high redshift objects. They match much better than nearby galaxies to the H2 region loci. But it's an issue that not much we can do.
So, Chuck, whenever I listen to people who study AGN, they always say, it looks super solar. Solar, the metallicity. And the guys who study the iron line sometimes say, I need 10 times solar.
Yeah.
So, is it that they are doing their analysis wrong, or is it a different part of the galaxy?
I'm not an expert on what exactly they're doing, but I think it's much more uncertain the way that you have it. I mean, it's possible. We're talking about physically much smaller regions, so I guess in principle it's possible, but it doesn't seem very likely a priori to me. But I don't know enough to say it's wrong. I suspect it might be.
Yeah, frankly, I don't even know whether they're looking at the oxygen or the iron. And they make these statements.
Yeah, this is based on broad emission line
Yeah.
relative intensities of that, that it's hard to model.
So this change in basically the oxygen to iron ratio between redshift, say, at O3 and today, has that even matured by now, or is it still evolving so that future
I mean, will
astronomers...
things go past solar abundance
Yes.
ratio? I don't know. I guess I hadn't thought. I think the fact that most things are just about out of gas, most galaxies are almost out of gas now, means that things can't change too much more. But
But you measure the oxygen in the gas you have.
true. I'd have to think about that. I don't know off the top of my head. But I guess there's no reason why it shouldn't continue to change, because the asymptotic, there's nothing magical about the sun. It's just kind of in an average place in an average galaxy. But the abundance, everything in the local universe has essentially solar abundance ratios in gas, where they're forming stars and today. And that's the problem. Like even Lyman break analogs, they have a longer star formation history just by virtue of the fact that there's been 12 billion years of the universe in between. And as long as it's anything that has an extended star formation history is more likely to have approached solar or it's similar to solar abundance ratios.
Well, I actually do have another question. You mentioned the binary stars produce the ultraviolet photons in greater abundance. And it's wondering why. I mean, what's binary?
There are lots of different mechanisms for doing it, and I'm not an expert on this, but from the massive star people I've talked to, so one way is that you actually have binaries where the more massive, so the winds are all weaker because the iron abundances are lower, and so they look kind of like Wolf-Rayet stars, but they don't have the metal lines associated with them. They have helium-2 broad lines from the winds. And you basically have lower mass loss rates, but you still have things that reach the end of their evolution, and you can suddenly dump huge amounts of mass from the more massive, more rapidly evolving star onto the less massive one, and it can't do anything about it. And there's very little, things tend to spin up in a situation because the mass loss is so low. Things basically just accrete mass and they spin faster. And it's the rapid rotation that it essentially makes nuclear burning much more efficient using all the material available in principle. It also it means that because you have this mass transfer, you can have the effective main sequence lifetime can be much longer, starting with massive for things that produce lots of ionizing photons over longer periods of time than they would be produced by single stars. So it's really this time scale thing that makes a big difference, because what we see is that everything needs the hard spectrum. It's not just the odd galaxy with a star cluster that's just going off and you have a few Wolf-Rayet stars. It's that it has to be on all the time. And it's very difficult to do that. There are spectral features that appear in every spectrum that are only produced for very short special times in local stellar populations. And so there are probably other ways of, if you just you just say, I don't care how it happens, but I'm going to make all the stars rotate at 600 kilometers per second or something like that, then the same kinds of things would happen. But it's the kind of thing where they're constrained by the known binary fraction among massive stars, and that seems reasonably well established now. It may be controversial, and I'm not aware of it. But there are lots of things that all go in the same direction, and all having to do with mass loss rates that are lower because of the lower iron abundances, and that makes the behavior in binaries very different.
Okay, we'll take one more question.
Yeah, I wanted to challenge your point about that everything at local universes, all the gases, solar, alpha to iron, because it's true on average. But if you look at individual galaxies, or for instance, you had slow star formation, and it reached the asymptotic ratio, which is solar, and then something happened, like a tidal interaction that boosted star formation, or it hit something like galaxies and clusters. Then what happens is you have very strong starburst over a short period of time, and it actually enriches it in alpha elements much higher.
Yeah, I can believe that, but it would happen a lot less frequently in the local universe.
In the LMC, the local star clusters at 100 million years or below 50 to 100, if you use alpha elements as proxy to oxygen, they have alpha-enhanced populations, while the ones that are 1 to 2 billion years old, which were this more or less quiescent stage, that's solar.
Yeah, I think it's a manifestation of the same effect. It's just that you have to have more special environments locally to have it. It basically means you have to form a large, more stars than have ever formed in that location happening all at once.
Okay, let's thank our speaker again.